Hi, I'm Billy. Today I'm going to be talking about our work with modeling password guessability using neural networks. And so this was work with my colleagues at Carnegie Mellon. And this work is about how we used neural networks to develop more accurate and more practical methods for password guessing. And so we keep hearing that passwords are dead, but most of us use them every day. And so they likely aren't going anywhere anytime soon. And something important to password security is accurately measuring the strength of passwords. So there are many situations where you might want to do this, like Dan showed, when the user is creating a password to give feedback, or after you already have a set of passwords to decide, for example, if passwords created under one password policy are stronger than those created under another. And so to measure the strength of passwords, we often turn to modeling how many guesses it would take attackers to guess a password using different guessing methods. There have been a variety of different guessing methods proposed and studied. I'm going to give you some background on current guessing methods now. So John the Ripper and Hashcat are two popular password cracking tools used in practice. They work by taking a list of dictionary words, which might include previously seen passwords and natural language words, and then transform them using mangling rules. And so the list of mangling rules is fed to each dictionary word to create a list of passwords. So for example, one dictionary word might be the word password, and one rule might be append 2 digits. So this would generate all combinations of 2 digits. Markov models have also been studied for use in password guessing models. They work by deriving statistical properties from text by counting what characters are likely to follow other characters. And probabilistic context-free grammars are another popular statistical method for password modeling. They work by representing passwords as different structures. So for example, L8D2 means passwords that start with 8 lowercase characters and end in 2 digits, and then generating passwords that match those structures. So both the Markov models and PCFGs attempt to model passwords using statistical methods about what characters or patterns are likely to be present in passwords. So typically they take some training data, and recent work has been done showing that they're both very accurate models for passwords. And all of these methods are attempting to solve what is close to a natural language processing problem. So it's how do we generate strings of text that humans would create? And passwords are similar in many ways to natural language. So another thing common to all of them is that they're trying to make very accurate guesses and trying to make guesses quickly. And so I just showed you some examples of guessing models. One important reason we model guessing attacks is to give password feedback. And so an example of something we can do with the results of guessing models is that we can put them into a password meter to encourage better passwords. We might also want to assess password security in the context of a research study or proactive password auditing. Okay, so this leads us to our main research question. We wanted to see if we can generate more accurate guesses for passwords. We also wanted to know if we can do it quicker or smaller. So the existing approaches that I showed you often take hours or days to give results, and model sizes can be in the hundreds of megabytes or gigabytes. And so for a lot of proactive password checking, you do this on a giant server with lots of memories and cores, and for the most part what's being done in browsers is inaccurate, as Dan just showed, and with ZXCVBN being the main exception to that rule. And so accuracy, speed, and size of the model are all important for making practical predictions. And so we chose to use the approach of neural networks. So neural networks are a machine learning method that works on tasks related to processing natural language. So for things like, recently they've been used as the basis for many technologies, like you may have heard that neural network-based technologies beat human champions at the game of Go. They've been used in a lot of classification problems and a lot of natural language processing tasks, like translation or handwriting. So we thought that they might be useful here too. And so now I'm going to show you how we designed and built our neural network password guesser to adapt neural networks to our problem of guessing passwords. And then I'm going to describe how our best performing neural networks compare to the existing guessing methods like PCFGs and Markov models that I mentioned earlier. And I'm also going to talk about how neural networks can be used for more effective real-time password feedback on resource-constrained devices. So when we measure password strength, we typically try to guess passwords and see how many passwords it takes to get a password. And so I'm going to show you how we actually generate candidate passwords using a neural network now. And so the classical forms of neural networks typically only classify text into different groups. But the machine learning community recently showed how you can use them to generate text. And so before I show you how to generate text using a neural network, I want to walk you through the related problem of predicting the next character of a password. So for example, if we're given a password fragment like passw, we might want the neural network to tell us that the most likely next character is a lowercase o, a 0, or an uppercase O, or something else. And so these are the characters that we're predicting using the previous characters in the password. And so now this is actually a classification problem. So our classes here are the predictions of the next character. And so we can use the neural networks to do this. And to train the neural network, we give it real password prefixes and ask it to predict the next character. And so that was at a high level how you predict the next character. Now I want to show you how you use that to generate passwords using this method. And so at a high level, what we're going to do is repeatedly predict the next character to generate a single password. And in practice, for a real guessing attack, you might want to enumerate all passwords above a certain probability threshold. But for now, I'm just going to show you how to generate a single password. So let's suppose we're starting from scratch. We have an empty string as the prefix, and the probability that you have that empty string is 100%. So you can use the neural network to predict the probability of the next character for the empty string. And we need to also allocate some probability that the password is going to end at this point. And so let's generate a likely password and start with C. Now we know that C as a prefix has a 5% chance of happening, and we can predict the next character again. And maybe it looks like this. And we can choose another likely letter, and we can do it a few more times. And so this keeps going until you end the password by multiplying by the probability that the password's going to end. And so now we've guessed a password, and we know its probability according to the network. So this is very similar to the way a Markov model does it, except the prediction step is a lot more expressive than a Markov model because we're using a neural network here. And so the network can approximate learning higher level things about passwords other than just counting the most frequent n-grams. So for example, one of the things that it might be able to do is take into a variable amount of the predicting text other than that a Markov model can't, or learn higher level features like how to count the length of a password, or that vowels often follow consonants. And so we can do this for as many iterations as we want and build up large numbers of passwords and then sort by the probability. So this is how you can get the neural network to create guesses of passwords for you. You can even remove passwords that don't adhere to a specific policy. So before I go on, I want to talk about password policies. In this work, we examine passwords from a variety of different password policies. I'm going to introduce some of them to you now. We looked at a common policy where passwords are only required to be at least 8 characters. Here are some examples of those passwords. We also looked at a policy that requires more character classes. So for character classes here are uppercase, lowercase, digits, or special characters. And here are some examples of those types of passwords. This is also another commonly used policy in practice. In addition to those two common policies, we looked at policies with longer length requirements because prior work from our group found them to be just as usable and more secure than the commonly used policies. And so as the ability to crack passwords increases, we might find more people moving to these longer policies. But one of the ones we looked at required at least 16 characters, and so here are some examples of those. We also looked at a longer policy that balances the length and complexity requirements, and 3 class 12 is an example of that. So now I'm going to talk about the design space and the experiments for our neural network password guesser. So neural networks are a huge area of ongoing research in the machine learning community, and there's a large design space of what's the best way to train them. We experimented with some aspects of the design space that we thought would be most impact the guessing accuracy, but it's impossible to exhaustively experiment with every conceivable dimension. And what you can do with neural networks seems to change every day, so I'm going to describe our experiments. So we needed to decide how large of a model to use. So I previously mentioned that existing password guessing approaches often require models on the order of gigabytes. And so we tested different size neural network models here to see if we could use a smaller model to estimate password strength with reasonable accuracy. And so larger models have more parameters that tell you how to compute the probability of the next character and are more expressive, but could overfit the data. So we looked at a 3 megabyte model and a 60 megabyte model. You could look at lots of points in between those two, but we chose the small one as something roughly the size that could be sent to a browser, and I'll talk more about that later. But the larger one was more limited by how much we could reasonably compute on our hardware. We also examined a specialized method of training called transference learning. And prior work has shown that having more training data leads to more accurate password guessing. So unfortunately, for a lot of the novel password composition policies, we don't have large amounts of training data. And we thought that transference learning might help. And so the idea of transference learning is that you would be able to train what one network learned and transfer that to another network. It's commonly used to deal with data sparsity. So for example, in our training data, we have lots of passwords that match a 1 class 8 policy, roughly 50 million, but many fewer that match a 3 class 12 policy, roughly 50,000. So if we only train a network on those 3 class 12 policies, it's going to guess worse than a network trained on all of the 1 class 8 because it's seen fewer examples. And so ideally, we would be able to train a network on all passwords and then transfer what that network learned to a specialized network for 3 class 12 passwords. We also experimented with including natural language non-password data in the training sets and using different training sets. So prior work and other guessing methods showed that using natural language dictionaries can improve guessing intuitively, especially for longer passwords that are commonly made up of words and phrases. We tested a number of other design dimensions, which we discuss in more detail in the paper. And so now I'm going to describe how we tested both our neural networks and the other approaches. And at a high level, we used each method to generate a list of to guess a list of test set passwords and then measured the number of correctly guessed passwords. For our training data, we used a variety of leaked password sets, and we had multiple sources of test data. So we used passwords that people created in the context of Mechanical Turk studies about passwords from previous work in our group. This allows us to look at many non-standard password policies created in a controlled environment. And we also used real leaked password set data from the 00 web host leak, which wasn't included in our training data. And so then we used a new technique of guess number calculation introduced by other researchers at CCS last year that takes advantage of Monte Carlo techniques to estimate accuracy for large numbers of guesses. And so we tried training the neural network along the different dimensions of the design space that I showed you earlier. And so the experiments I'm about to show you are about how do we train the best neural network guesser. So they're comparing one version of the neural network guesser to another. So first I'm going to show you how to read the graphs of our results. I'm going to show you lots of graphs that look like this. They show how many correct guesses different methods make at different numbers of guesses. So the x-axis shows how many guesses were made. And the y-axis shows the percent of passwords guessed at that guess number. So more accurate guessing methods are higher. So for example, here the green line is more accurate than the orange line. And so we found that transference learning improves the accuracy of guessing. So this experiment was done with 1 class 16 data, and the effect was significant. So for example, at 10 to the 15th, we have a 15% of passwords guessed versus 22%. So that's almost a 50% increase in guessing effectiveness, which is very good. In contrast, we found that including natural language data with the real password training data didn't help. So we did this experiment also with the 1 class 16 passwords, which we thought would most benefit from the natural language because those passwords have lots of words and phrases in them. We found that our larger network in general performed better than our smaller network. However, the surprising thing is that it often wasn't that much better. So often the smaller model worked nearly as well as the larger one. So here the dotted line here is the larger network, and especially for the 2 shorter policies that we tested. However, it was potentially a larger difference for the longer 1 class 16 policy. And sometimes the larger network wasn't as good. So for the web host passwords, for example, the smaller network actually worked a little bit better. You may not be able to see the purple lines because they overlap with the other ones, but it's likely that a network size in between the two would work better here. And so at the end of the experiments I just talked about, we had a configuration of a neural network that performed the best compared to other variations on neural network training that we tried. So now I want to show you how our best performing neural networks did compared to the best performing existing methods like PCFGs and Markov models. So here's a graph showing the other guessing methods that we use. These measurements come from the best tunings of these algorithms that we could find in the literature and from our USENIX paper last year. And you'll notice that John the Ripper and Hashcat stop earlier than the others. This is because they were calculated by enumerating guesses rather than the Monte Carlo estimation that can go to very high numbers of guesses. And so here's our neural networks. And they do better than anything else, especially at high guess numbers. And we believe this is because the neural networks are particularly good at guessing novel passwords. And here the black line is the minimum guess across all approaches. So this is an approximation for the sum of all the methods, including the neural networks. So should we just use neural networks? Well, not really, because other guessing methods guess slightly different passwords, and so using all of them guess more passwords than just neural networks. But if you were going to use a single method, then it seems likely that neural networks would be the best choice. And so for the more specialized 4 class 8 data set, the trend is the same with even better performance. And for very specialized policies, it's even better. So here's the 3 class 12 data. At 10 to the 16 guesses, neural networks are guessing roughly 45% of passwords, while the next best method is guessing roughly 30%. So this is also like a 50% improvement compared to the next best single method. And this trend holds across all of our data sets to varying degrees. And we found that the neural networks seem to do best at high guess numbers and with more specialized password policies. And so we just saw that neural networks could guess passwords better than any other single method. Now I want to switch gears to talk about how we use them for practical real-time password feedback. And so as I mentioned, often that feedback is in the form of a meter that tells people how strong their password is. And we'd like this feedback to be accurate with respect to how hard attackers find it to guess passwords. So when it says the password is weak, it's likely to be guessed, and when it says it's strong, the password is not likely to be guessed. However, the current state of the feedback, with the exception of ZXCVBN that you just heard about, is that you either get very accurate feedback by performing a cracking attack with multiple guessing methods, or you can get very quick feedback that's not as accurate by doing things like counting the number of different character classes at the length of the password. And so there's a need for feedback that's quick enough to be done in real time, but also practical enough to be used on client machines, and as accurate as performing a real guessing attack. And so if you look at the other guessing methods, they take gigabytes of disk space, and so this is not practical for getting real-time feedback on a client machine. You're not going to be able to give this to a web browser to send to people when they sign up for your service. But the interesting thing about our best performing neural networks was that it was very small, like 60 megabytes, compared to the gigabytes. And when you consider even the smaller version was 3 megabytes, that's something that's more in the range that you can send to a client, and that still performed very well. And so we thought maybe there's hope for compressing an accurate model for use in a web page this way. The other thing is that they typically take hours or days on highly parallel servers using over like upwards of 50 cores in our experiments. This is also something that's not likely to happen in the context of real-time password feedback. And so this leads us to our other research question. We wanted to see if neural networks could be used to give real-time password feedback on resource-constrained machines. And the reason we wanted to do this is to combine the accuracy of modeling password guessing in a principled way with fast real-time feedback. The other benefit of using neural networks is that you can retrain a new one for different policies or for specific sites without coming up with a bunch of manual rules. And so these are the targets we set ourselves for performance. It has to be small, roughly less than a megabyte. And so the average web page now is roughly 2 megabytes, and it's always growing. So in comparison to that, 1 megabyte isn't a lot, especially when you consider that you're only going to load this when a user creates a new password. It also has to give low latency feedback. So the threshold of recognition is roughly at about 1/10 of a second. So something less than that would be good. And we have to do this while executing in JavaScript, which is sometimes challenging to make fast. And it should be accurate. And by accurate here, I mean accurate to within a rough order of magnitude. So typically, these results are presented in a highly bucketized way to users, like strong or weak. So we're looking for something that is within the same order of magnitude. And so our approach to making meters small is first we started out with our small neural network. Then we quantized the parameters of the model, only storing the first 3 decimal places. So the parameters of the model are the numbers that define how to predict the next character. And so this means only storing the first 3 decimal places rather than storing the full 7 to 8 decimal places for a full floating point number. And so then we compress the model using existing lossless compression native to all browsers like gzip. And we did a few other things that you can read about in more details in the paper, and our final model was 850 kilobytes, which is less than our target. And so then to make our meter fast, first we pre-computed inexact guess numbers. So the expensive process is computing, in the methods that I just showed, is computing guess numbers. But the probabilities are a lot easier to compute. And so we pre-compute the guess numbers. And then we cache intermediate results. So to calculate the probability of a password, you really need to make one calculation of the neural network for each character. But however, the common case is adding or removing a character for the end. So that first computation stays the same, and so you can cache those. And we also run it on a separate thread to avoid freezing the UI. So in the common case, we got the response time to be on average 17 milliseconds, which is well below the threshold of recognition. And so we wanted to do all of this without compromising too much on accuracy. And so many of the modifications that I was telling you about for size and speed reduce the accuracy of the system. So we measured how much these changes affect the accuracy. And so here's a guessing curve of the small neural network on the server. And here's the browser implementation. And so you may not be able to see this, so let's zoom in. You can see the little sawtooths here result from pre-computing the guess numbers. And so notably, like you can see here, this quantization can be likely safe in that you might underestimate the strength of a password, but not overestimate it. So you can notice that the orange curve is, for the most part, completely below the green curve. And so we discuss more details about the accuracy of our client-side guesser in the paper. So in summary, we demonstrated that how to build a password guesser using neural networks. And we showed how you can use it to do better than existing guessing methods. And finally, we also showed how you can use it to create fully client-side password feedback. And so we released the code, and you can find the link in the paper or go to github.com/cupslab. So thank you.
We have time for questions.
Hi, Florian Tramer from EPFL. To make your model smaller, have you looked at a process called distillation? So this is something rather new in machine learning, where been proposed by people at Google, where you first train a large neural network and then try to train a smaller neural network to behave like the larger one. And apparently you can get very good results using these kind of techniques.
I'm not familiar with that one specifically, but we did something related where we tried to tutor a smaller network with a larger one, and we didn't get great results from that. But maybe if I'm more familiar with that work specifically, I could say more.
Hi, Antoine Lemay from École Polytechnique. I'm wondering, how frequently do you think you would need to retrain your model for your estimators? Because every time you retrain, you would have to patch the system. So how frequently do you need to patch to have the model stay accurate with the new guessing method?
So ideally you would only have to train it once for the system. If the passwords that are being used in the system keep changing, then it'll depend on how fast the passwords being used change for it to stay accurate.
Rick Farrow. I'm curious. In one case, your 3 megabyte model actually was more accurate than your 60 megabyte model. Do you have any idea why?
So we think that it might be related to the type of training data that was used for that specific test. The web host passwords were a little bit different than the training data, and so it might be an interaction between that. It's hard to speculate on.
It is hard to speculate on neural networks, and I guess in general, I was surprised that there wasn't more difference between the two models. Did you try any other larger models than the 60 megabyte model?
We didn't try larger ones, but
for the reason you stated, yeah. Just curious. Okay, yeah. Thank you.
We got time for one more quick question. Quick, though.
Rich Johnson, I'll make it really quick. Have you considered focusing a neural network in on OCL hashcat or common generic attacker tools to defeat those specific threats?
I'm sorry, could you say that again?
Specific attackers, particularly pen testers, will use OCL hashcat or John the Ripper in default mode. Have you considered doing a neural network that's focused on defeating those threats to take away 90% of your password breaks and not bother users with the attackers who are really going to do their homework and pick good word lists?
So you're asking about training a neural network that mimics a hashcat or a... no, we haven't looked at that, but that would be a good thing to look at for future work.
All right, great. Why don't we thank speaker again?